Right now, everything you have ever known or loved is being pulled apart. Not slowly, not eventually. Now. This second. The atoms in your body, the walls of the room you are in, the planet under you, the galaxy above you. All of it is embedded in a fabric that is stretching in every direction simultaneously. And that stretching is accelerating. The universe is not just expanding. It is expanding faster today than it was yesterday, and faster yesterday than the day before that. Whatever is causing it has been pushing outward for nearly 14 billion years, and we cannot see it, cannot measure it directly, and cannot explain it. We have given it a name, dark energy, but naming something is not the same as understanding it. The name is a placeholder for our ignorance, a label on a door we have not been able to open. You feel none of this. Your coffee sits still in its cup. The room is quiet. The air is still. And yet, at this moment, galaxies that contain hundreds of billions of stars each are receding from us at velocities that exceed the speed of light. Not because they are moving through space faster than light can travel, but because the space between us and them is growing. Space itself is the thing that is moving, and whatever is making it move is the dominant force in the universe, more powerful than gravity, more pervasive than matter, more mysterious than anything physics has encountered before or since. If this is the kind of investigation that interests you, subscribe now. The investigation begins here. Let us start with what we know. The universe is approximately 13.8 billion years old. That is confirmed. It began in an event of incomprehensible density and heat, a moment when space itself came into existence and immediately started to expand. Everything that exists, every star, every planet, every atom that has ever formed a thought or a breath, was compressed into a region smaller than a proton, and then it was not. In the first fractions of a second, space expanded faster than the speed of light. This is not a violation of physics. The speed of light limits how fast objects can move through space. There is no limit on how fast space itself can expand. The fabric stretched. Objects embedded in it were carried along. This is established. This is not speculation. The data from the cosmic microwave background, a faint hiss of ancient light that fills the sky in every direction, confirms it. When astronomers point any telescope at any patch of sky and look at the faintest, most distant things they can detect, everything is receding. Every direction, every magnitude. The recession is universal. You are at the center of it, in the sense that every observer in every galaxy in the universe sees the same thing. Everything else moving away. This is not because we occupy a special location. It is because there is no special location. The expansion is built into the fabric, and every point in the fabric is expanding away from every other point simultaneously. The distribution of galaxies across billions of light years confirms the expansion. The abundance of light elements like hydrogen and helium, forged in the first 3 minutes after the Big Bang, confirms the temperatures that must have existed then. The universe began. It expanded. This is not in question. For roughly the first 9 billion years, that expansion slowed down. This was expected. Gravity, the force that pulls matter together, should slow expansion. Think of it like throwing a ball straight up. The ball rises fast, slows, and if you throw it hard enough, it escapes. If not, it falls back. In the early universe, everything was flying apart with enormous energy from the initial event. But gravity was supposed to act as a brake. Cosmologists expected to measure a universe that was expanding, yes, but decelerating as time passed. Many believed that at some point gravity might even win. The universe might halt its expansion and begin to contract. Everything falling back toward everything else in a final catastrophic implosion. The Big Crunch. The end not with a cold, dark emptiness, but with a fiery, crushing reversal. They built instruments to measure this deceleration. The tools they chose were Type 1a supernovae. These are stellar explosions, the deaths of particular kinds of white dwarf stars that produce a characteristic peak brightness. Because the peak brightness is known, you can calculate the distance to any type 1a supernova. And because the light is redshifted by the expansion of space, you can calculate how fast that region of space was expanding when the supernova exploded. By comparing supernovae at different distances, different moments in the history of the universe, you can map the expansion rate over time. You can see whether the universe was decelerating, as gravity would predict. Two independent teams built this measurement in the 1990s. The High Z Supernova Search Team, led by Brian Schmidt, with Adam Rees as the lead data analyst, and the Supernova Cosmology Project, led by Saul Perlmutter. Both teams were looking for the same signal, a universe whose expansion was slowing. Both were looking at supernovae billions of light years away, at light that had been traveling since the universe was less than half its current age. Both teams found something different. The distant supernovae were dimmer than expected. Not by a lot, but by a consistent, systematic amount that could not be explained by measurement error. The galaxies in which those supernovae exploded were further away than they should have been if the expansion had been decelerating. The light had taken longer to reach us than it should have, which meant space had been expanding faster than the models predicted. The universe was not decelerating, it was accelerating. The expansion is speeding up. The results from both teams were published in 1998. Both teams reached the same conclusion from completely independent data and completely independent methods. The universe had indeed been slowing down for its first several billion years, as expected, but approximately 5 billion years ago, something changed. A new term in the energy budget of the universe began to dominate, something with the property of pushing space outward faster and faster, something that behaved in the exact opposite way to matter. Where matter is diluted as space expands, this thing's energy density per unit volume remained constant, or possibly even grew. As space expanded, this thing did not weaken. It persisted. It accumulated. It drove the expansion faster. They called it dark energy. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011. The discovery was that real. This is confirmed. This is what the data says. But we need to be precise about what the word discovery means here. They did not discover dark energy in the sense of finding a particle or identifying a substance. They discovered a gap, an accounting problem. You can measure the total energy content of the universe by observing its geometry. The curvature of space-time, which depends on how much energy is present. You can separately count up all the matter you can observe, and the difference between the total and the observable gives you something. A remainder. A number that must be there to make the equations balance. That number accounts for roughly 68% of everything in the universe. Add in dark matter, the invisible, gravitationally active substance that surrounds and fills galaxies, accounting for about 27%. And you are still missing the majority. Ordinary matter, every atom in every star, every planet, every human body, every ocean, every breath, accounts for approximately 5% of the universe. The other 95% is either dark matter or dark energy, and of that 95%, dark energy is the dominant share. More than 2/3 of the universe is made of something we cannot see, cannot collect, cannot identify, and cannot explain from first principles. What is dark energy exactly? This is where the investigation becomes uncomfortable. We do not know. There are candidates, frameworks, hypotheses. Some are elegant, some are disturbing. None are confirmed. And the range of outcomes they predict for the future of the universe spans an enormous space. From a slow, cold, empty death to a catastrophic ripping apart of atoms and space-time. The most prominent candidate is called the cosmological constant. To understand it, we have to go back to Albert Einstein. In 1915, Einstein published the field equations of general relativity. These equations describe how matter and energy curve spacetime, and how curved spacetime tells matter how to move. They were, and remain, the most accurate description of gravity ever written. But in 1917, Einstein had a problem. He believed, as nearly all scientists of his era did, that the universe was static, not expanding, not contracting, just sitting there, a fixed and eternal arrangement. But his equations did not produce a static universe. They produced a dynamic one that would either expand or contract. Left alone, his equations predicted motion. To prevent this, he added a term to his equations, a constant of integration that could be freely chosen. He chose it to exactly counterbalance the gravitational pull of all the matter in the universe, producing a static solution. He called it the cosmological constant. The symbol is the Greek letter lambda. For 12 years, Einstein's static universe with the cosmological constant stood. Then, in 1929, Edwin Hubble published his observations of distant galaxies. Every galaxy was receding. The universe was expanding. The static model was wrong. Einstein no longer needed his cosmological constant to prevent collapse. Because the universe was not collapsing, it was flying apart. He called the introduction of the cosmological constant his greatest blunder. He removed it from his equations. But the equations did not forget it. After 1998, the cosmological constant returned. Not as a device to produce stasis, but as a description of what we now observed. In general relativity, you can add a constant energy density to space-time itself. A property not of matter within space, but of the fabric of space. Energy that exists wherever space exists, regardless of whether anything else is present. This energy has a specific property. Unlike matter, which has positive pressure, the cosmological constant has negative pressure. It pushes rather than pulls. As space expands, the energy density of the cosmological constant remains the same. There's simply more space containing the same energy per unit volume. Total energy increases with expansion. The more space there is, the more dark energy there is. The more dark energy there is, the faster the expansion. A self-reinforcing driver with no natural limit. And this model fits the data. It fits the supernova measurements. It fits the cosmic microwave background. It fits the large-scale structure of the universe. It fits the Hubble constant measurements, at least to the precision we had before the Hubble tension emerged. Lambda, CDM, the cosmological constant plus cold dark matter, is the standard model of cosmology. It is, by most measures, the most successful scientific model of the universe ever constructed. But it has a problem. A devastating problem. A problem that sits at the intersection of the two greatest theories in physics, general relativity and quantum mechanics, and reveals that, in at least one crucial sense, we do not understand either of them. The problem is the energy of nothing. In quantum mechanics, the vacuum, the state of empty space with no particles in it, is not nothing. It is the lowest energy state of every quantum field that exists. And in quantum field theory, the vacuum energy of each field is non-zero. It is a fundamental consequence of Heisenberg's uncertainty principle. If you know the exact energy of a system, if it is exactly zero, then by the uncertainty principle, you cannot know anything about its time evolution. But the vacuum has definite properties over time, so its energy cannot be exactly zero. It must fluctuate. Virtual particles appear and annihilate. Fields vibrate at their ground state. The vacuum hums. This is not hypothetical. The Casimir effect demonstrates it directly. Take two uncharged, conducting metal plates and place them extremely close together in a vacuum. A force develops between them. Not an electromagnetic force. The plates are uncharged. Not gravity. The force is too strong at these distances. The force comes from the vacuum. Between the plates, only certain wavelengths of virtual photons fit. Outside the plates, all wavelengths are present. The imbalance in vacuum energy density creates a pressure that pushes the plates together. The Casimir effect has been measured. It matches quantum field theory predictions. The vacuum has energy. This is confirmed. Now ask, how much energy? Quantum field theory calculates the vacuum energy density. The answer, before any theoretical tricks to reduce it, is approximately 10 to the power of 113 joules per cubic meter. The dark energy we measure has a density of approximately 10 to the power of minus 9 joules per cubic meter. The discrepancy is 10 to the power of 122, a 1 followed by 122 zeros. To calibrate your sense of how large this is, the number of atoms in the observable universe is approximately 10 to the power of 80. The discrepancy between the theoretically predicted vacuum energy and the measured dark energy is larger than the square of the number of atoms in the observable universe. It is larger than any number that has ever appeared in a physical calculation, and turned out to be wrong by this margin. It is larger than any number that has ever appeared in a physical calculation. Full stop. This is called the cosmological constant problem. It has been described by physicists as the worst prediction in the history of physics. The most precise theory we have, quantum field theory, tested to more decimal places than any other theory in science, predicts a vacuum energy that would make any universe it described incompatible with the existence of structure, incompatible with atoms, incompatible with chemistry, biology, thought, observation. If the quantum field theory prediction were correct, the expansion of the universe would be so rapid that particles could never bind into atoms. The universe would have been torn apart in the first fractions of a second after the Big Bang. Nothing would exist. The fact that anything exists at all, the fact that you are here to hear this, requires that the true vacuum energy is at least 120 orders of magnitude smaller than the naive quantum calculation predicts. Something is cancelling it, almost completely, almost perfectly, leaving only a tiny residue, and that residue is dark energy. We do not know what is doing the cancelling. We do not know why the cancellation is so extraordinarily precise. We do not know whether the residue is truly constant or whether it changes over time. This is not a small gap in our knowledge. This is a fundamental failure of our best theories to produce a consistent picture of reality. It does not mean general relativity is wrong. It does not mean quantum field theory is wrong. Both work extraordinarily well in their own domains. But they cannot both be right in the way we currently understand them, because when they speak about the same thing, the energy of the vacuum, they give answers that differ by a factor that is literally incomprehensible. There are physicists who believe the resolution lies in supersymmetry. In a perfectly supersymmetric universe, every known particle has a partner particle, a superpartner, with opposite quantum properties. The vacuum energy contributions of particles and their superpartners cancel exactly. The cosmological constant is zero, perfect, clean, explained, but supersymmetry, if it exists, is broken. The particles we observe do not have visible partners at the same mass. The symmetry is not exact in our universe, and broken supersymmetry still cancels some of the vacuum energy, but not enough. The remaining vacuum energy after supersymmetry breaking is still many orders of magnitude too large. The Large Hadron Collider searched for supersymmetric partners for over a decade. It found none at the energies that would have made the supersymmetric explanation most natural. This does not rule out supersymmetry. It could exist at higher energies than the LHC can reach, but it makes the case harder to make, and it makes the cosmological constant problem harder to solve. There is another candidate for dark energy, not a constant, but a field, a dynamic field that evolves over time. Something that was different in the early universe and is different today. Physicists call it quintessence. a hypothetical scalar field that permeates the universe and whose potential energy drives the acceleration of expansion, but whose value changes with cosmic time. In a quintessence model, dark energy is not a fixed property of the vacuum. It is a field, like the electromagnetic field or the Higgs field, with a value at every point in space and time. That value changes as the universe evolves. The pressure and density of dark energy, described by the equation of state parameter, W, would not equal exactly -1 as the cosmological constant requires. It would be close to -1, but evolving. Slightly different in the early universe. Slightly different today than it will be in the future. If dark energy is quintessence rather than a cosmological constant, the fate of the universe becomes harder to predict. The field might continue to drive acceleration, or it might eventually slow. It might even reverse. Quintessence models can produce dark energy that eventually becomes repulsive in a different sense, causing a contraction. The future timeline of the universe is entangled with the identity of dark energy. Recent observations have offered a hint. The Dark Energy Spectroscopic Instrument, DESI, is a spectrograph mounted on the Mayol telescope at Kitt Peak National Observatory in Arizona. It measures the spectra of millions of galaxies, tracking the acoustic oscillation scale across cosmic history to map the expansion of the universe. Data from DESI, released in 2024 and refined through 2025, shows a hint, not yet definitive, but statistically meaningful, that dark energy is not constant. The equation of state appears to have shifted slightly between the early universe and today. The signal is at the level of 2 to 3 sigma. Suggestive, but not yet conclusive. But it is consistent across different subsets of the DESI data. It is consistent with results from some, but not all other cosmological surveys. Multiple teams are now looking for the same signal independently. If it holds, if the next generation of data confirms that W is evolving, then the cosmological constant is ruled out. Dark energy is a field, not a fixed property of the vacuum, and the universe's future becomes genuinely uncertain. Let us follow the consequences of what we know now, and what we might know depending on what dark energy turns out to be. The universe has a fate. It has multiple possible fates, depending on which version of dark energy is correct. And the range of those fates spans from vast cold emptiness to something far more violent. In the most benign scenario, the cosmological constant scenario, the universe expands forever at an accelerating rate. Over hundreds of billions of years, galaxies outside our local group recede beyond our observable horizon. Their light, emitted today, is already committed to never reaching us. The space it must cross is growing faster than the light can traverse it. In roughly 100 billion years, the only galaxies visible from our position will be those gravitationally bound to our local group. The rest, hundreds of billions of them, will have vanished behind an expanding horizon of invisibility. Not destroyed, not gone, just unreachable, permanently beyond the reach of any signal we could ever send or receive. For any civilization that exists in our galaxy 100 billion years from now, the universe will look empty. Their astronomers will see a small cluster of galaxies surrounded by absolute darkness. They will have no evidence that the universe contains any other galaxies at all. They will look up and see only their neighbors, and beyond that, nothing. If they develop cosmology without access to the relic light and structure that we can see today, they may conclude that they exist alone in an otherwise empty universe. We would know better. But we are only here to know it because we arrived in time, because the evidence is still visible. Continue forward. In about 2 billion years, the Milky Way and Andromeda will begin their merger. Andromeda is approximately 2.5 million light-years away, and approaching us at about 110 kilometers per second. The collision will take hundreds of millions of years to complete. It will not destroy either galaxy in the sense of blowing it apart. Stars are too far apart for individual stellar collisions to be common. but the gravitational interaction will distort and reshape both galaxies. Stars will be flung into new orbits. The spiral arms will be torn and thrown. Over hundreds of millions of years, the two galaxies will pass through each other, pull back together, and eventually merge into a single, larger, elliptical galaxy. Astronomers call the result Milkomeda. The supermassive black holes at the centers of each galaxy will spiral toward each other as the merger completes. Their eventual collision will release gravitational waves of extraordinary power, detectable, in principle, from across the observable universe by any instrument sensitive enough to measure them. This merger is local, a gravitational event. It does not change the broader trajectory. The universe is still accelerating. Milkomeda will still see the rest of the universe receding beyond the horizon. Life on any planets that survive the merger, and there may be many, will still eventually find themselves in a universe that appears to contain only their galaxy and a few gravitationally bound neighbors. Go further. 1 trillion years from now, the last red dwarf stars begin to exhaust their hydrogen. Red dwarfs are the smallest, coolest, most common stars in the universe. They burn slowly, carefully, cycling their fuel through their interiors so thoroughly that they can sustain fusion for trillions of years. A red dwarf with a mass 1/10 of the sun's will burn for approximately 10 trillion years before exhausting its fuel. But eventually they too go dark. The universe's last generation of stars will die. Not in explosions. Red dwarfs do not explode. They simply cool and fade, becoming brown dwarfs and then black dwarfs as they gradually radiate away their residual heat over unimaginably long timescales. After the last stars die, the universe enters what physicists call the degenerate era. The only objects with any significant structure are the remnants of dead stars. White dwarfs cooling toward absolute zero, neutron stars spinning down and radiating their rotational energy into space, and black holes. The galaxy, if any gravitationally bound structure still recognizable as a galaxy persists, is lit only by the faint infrared glow of cooling stellar corpses. Black holes persist longer. A stellar mass black hole, the remnant of a star several times more massive than the Sun, evaporates via Hawking radiation over approximately 10 to the power of 67 years. To calibrate this, the current age of the universe is roughly 10 to the power of 10 years. A stellar mass black hole lasts for 67 orders of magnitude, longer than the current age of the universe before evaporating. A supermassive black hole, millions or billions of times more massive, takes far longer still. The supermassive black hole at the center of our galaxy has a mass of about 4 million solar masses. Its Hawking evaporation timescale is approximately 10 to the power of 87 years. After the last black hole evaporates, there is nothing but photons, neutrinos, and electrons and positrons at such low energy densities that they will never interact again. The universe reaches a state of maximum entropy, maximum disorder. No gradients of temperature or energy that could ever drive a process. No work can ever be done again. Nothing can ever happen again. This is the heat death. The final state of a universe governed by thermodynamics and a constant dark energy. Cold, dark, infinite, silent, and permanent. This is the best case scenario. There is a worse one, and it emerges from a very small change in a single parameter. When we describe dark energy with an equation of state parameter W, the ratio of its pressure to its energy density, the cosmological constant requires that W equals exactly -1. Exactly. Not minus 0.99, not minus 1.01. Exactly -1. If W is greater than -1, say minus 0.9, dark energy has a different character. As space expands, the energy density of this dark energy decreases, just as the energy density of ordinary matter decreases with expansion. The dark energy weakens over time. The acceleration of expansion might eventually slow. This is sometimes called phantom-free quintessence. It leads to a slow expansion rather than a rip, and the ultimate fate resembles the heat death. But if U is less than -1, say minus 1.1 or minus 1.5, dark energy has a different character entirely. As space expands, the energy density of this dark energy increases. More space means more energy per unit volume. The expansion not only continues to accelerate, it accelerates at an ever-increasing rate. The expansion rate at any moment is always faster than the expansion rate at the moment before, and this has a specific terminal consequence. If the expansion rate is always increasing, then at some finite time in the future, the expansion rate becomes infinite. In a finite number of years, the rate at which space is being created between any 2 points becomes arbitrarily large. And gravity, no matter how strong, cannot hold structures together against an infinite expansion rate. But the rip does not happen all at once at the moment of singularity. It happens in stages, working down from the largest scales to the smallest, as the expansion rate passes the threshold at which gravity can no longer maintain various structures. The timeline depends on the specific value of W. In a representative model with a rip time of 22 billion years from now, here is the cascade of destruction. Approximately 1 billion years before the rip, the expansion rate has accelerated enough that galaxy clusters can no longer remain bound. The gravitational force holding clusters of galaxies together is overcome by the expansion of space between member galaxies. Clusters dissolve. Individual galaxies drift apart into the expanding void. The largest structures in the universe, the superclusters and filaments that span hundreds of millions of light years, are torn apart not by any explosion but by the simple relentlessness of expanding space. 60 million years before the rip, individual galaxies dissolve. The Milky Way, if it still exists in recognizable form, is pulled apart. The stars that have orbited the galactic center for billions of years drift away, each on its own trajectory into the expanding void. The galaxy does not explode. It simply ceases to be a gravitationally coherent structure. The stars disperse. 3 months before the rip, our solar system dissolves. The planets lose their orbits. The gravitational bond that has kept Earth circling the sun for 4.5 billion years is finally overcome. The planets drift free. Earth becomes a rogue body in a void that no longer contains any large structures. 30 minutes before the rip, Earth itself is torn apart. The gravitational and electromagnetic forces that hold the planet together, the bonds between rock and iron, the pressure equilibrium that sustains the interior, are overwhelmed. The planet fragments. Rock and metal disperse into a cloud of debris that expands into the void. 1 microsecond before the rip, atoms are torn apart. The electromagnetic force, the force that binds electrons to atomic nuclei, the force responsible for all chemistry, all molecular bonds, all biology, is overcome by the expansion rate. Electrons are stripped from atoms. Matter, in the sense of organized atomic structure, ceases to exist. At the moment of the rip, space-time becomes singular. The curvature of space at every point simultaneously becomes infinite. Space-time tears. The Big Rip is not a return to the initial singularity. It is a new singularity, one spread throughout the entirety of space, rather than concentrated at a point. Is the end not of any particular region, but of the fabric itself? This outcome is not ruled out by current observations. The measured value of W from all current datasets is consistent with -1, the cosmological constant, but it is also consistent with values slightly above and slightly below -1. The error bars encompass the phantom dark energy regime, where W is less than -1. The Big Rip cannot be excluded. The measurements coming from the next generation of instruments, DESI, Euclid, the Roman Space Telescope, the Rubin Observatory, are designed specifically to narrow the error bars on W. They will measure the expansion history of the universe with greater precision than ever before. They will measure the equation of state of dark energy at multiple epochs in cosmic history. If W is evolving, if it is different today than it was 5 billion years ago, they will see it. And the direction of that evolution, if it exists, will begin to tell us which fate we are heading toward. We do not yet know. That is the honest answer. The universe could end in a cold, gradual death over incomprehensible timescales, or it could end in a catastrophic rip in roughly 20 billion years, tearing apart every structure that exists, from galaxy clusters down to the electrons in your body. And we have not yet measured the universe precisely enough to know which. Now let us talk about what this expansion is doing to the knowable universe. Right now. Not in billions of years. Now. The observable universe has a radius of approximately 46.5 billion light years. This seems like a paradox. If the universe is 13.8 billion years old, how can light have reached us from 46.5 billion light years away? Because space has been expanding during the journey. The source of the most distant light we can observe was only about 42 million light years away when it emitted that light, 13.8 billion years ago. In the time the light has been traveling, the source has been carried to its current distance by the expansion of space. When we account for that expansion, the current distance to the furthest visible sources is 46.5 billion light years. Beyond that sphere, beyond 46.5 billion light years in every direction, lies the rest of the universe. We cannot see it. Light from beyond that distance has not had time to reach us. But in a flat, infinite universe with the structure the Standard Model predicts, it continues, indefinitely, for as far as you can imagine and further. The observable universe is not the universe. It is the portion of the universe that happens to be visible from our position at this moment in time. As time passes, more light reaches us from further distances, but only in a non-accelerating universe. In an accelerating universe, the situation is the reverse. Because the expansion is accelerating, our cosmic event horizon, the boundary beyond which emitted light will never reach us, is shrinking relative to the universe as a whole. Not shrinking in absolute terms. The physical distance to the horizon is increasing as the universe expands, but shrinking as a fraction of the total universe. Events happening right now beyond our event horizon cannot send any signal that will ever reach us. The light they emit will be carried away from us by expanding space faster than it can travel through space toward us. Think of it like this. You are standing in a river. Objects floating downstream past you are moving at a particular speed. As long as you can swim faster than the current, you can reach any floating object, no matter how far downstream it is. You just have to swim hard enough and long enough. But if the current speeds up continuously, there comes a point at which no matter how hard you swim, some objects will always be receding faster than you can approach them. They are not destroyed. They have not moved. The river just became too fast. You can never reach them. The cosmic event horizon is the downstream limit of the universe. Light emitted from sources beyond it cannot swim against the expansion and reach us. And because the expansion is accelerating, that horizon is a permanent feature of our universe, not a temporary limitation. Objects that are right now emitting light toward us, light we will one day see, are already beyond the event horizon, in the sense that if they emitted that light one moment later, it would never arrive. The photons already in transit will make it. Future photons from the same source will not. This is a fundamental limit on knowledge, not a limit imposed by technology or budget or time, a limit imposed by the laws of space-time itself. The structure of the universe, flat, infinite, accelerating, means that the set of things any observer can ever observe is finite, and is a diminishing fraction of the whole. And there is a corollary to this that is rarely stated explicitly. We are living at the best time in cosmic history to do cosmology, not in a vague, inspirational sense, in a specific, physical sense. The evidence that allows us to understand the origin and structure of the universe is currently visible to us. the cosmic microwave background, the echo of the Big Bang, the fingerprint of the early universe, the primary source of our knowledge about the first moments of cosmic history, is right there. It fills the sky. It has been mapped by COBE, by WMAP, by Planck, with increasing precision. It encodes the spectrum of quantum fluctuations that seeded every galaxy, every cluster, every void in the large-scale structure of the universe. It tells us the composition of the universe, ordinary matter, dark energy, to extraordinary precision. In a few trillion years, the cosmic microwave background will have been redshifted beyond any detectability, stretched by expansion into wavelengths so long that no imaginable instrument could measure them. The evidence will not be erased. It will simply be beyond reach. The galaxies we see today, hundreds of billions of them, spread across billions of light years, are still visible. Their light is still arriving. Their positions encode the acoustic oscillations of the early universe. Their clustering patterns tell us about dark matter and dark energy. They are the subjects of the most ambitious galaxy surveys ever attempted. In 100 billion years, most of them will be beyond the horizon. Gone not in the sense of destroyed, but gone in the sense of unreachable. A civilization that develops cosmology at that point will have access to only the local group, a few dozen galaxies. They will lack the evidence to understand that the universe ever contained more. The Big Bang will not be provable from the data available to them. We arrived at the right moment. We are seeing the universe at its most legible. And yet, there is a crisis in that legibility that we have not resolved. The Hubble tension. The Hubble constant is the number that describes the current rate of expansion of the universe. It tells you how fast two galaxies separated by a given distance are receding from each other due to the expansion of space. A higher Hubble constant means faster expansion. It also affects the calculated age of the universe. A faster expansion means a shorter time since the Big Bang. There are two ways to measure it, and they give different answers. The first method uses the early universe. The Planck satellite mapped the cosmic microwave background with extraordinary precision. From that map, using the standard model of cosmology, physicists calculated the Hubble constant. The answer was 67.4 kilometers per second per megaparsec. This means that for every megaparsec, roughly 3.26 million light years, of distance between 2 points, those points are receding from each other at 67.4 kilometers per second due to expansion. The second method uses the local universe. Astronomers measure distances step by step. First, they use parallax, the apparent shift of nearby stars as Earth orbits the Sun, to calibrate nearby distances with direct geometry. Then, they use Cepheid variable stars, whose pulsation period is directly related to their intrinsic brightness, to push further. Then they use Type 1a supernovae, calibrated against the Cepheids, to push to cosmological distances. The answer from this local distance ladder is approximately 73 kilometers per second per megaparsec. 73 versus 67.4. This sounds small. It is not. Both measurements have been refined by multiple independent teams over years. The error bars have shrunk. The disagreement has not. The statistical significance is now above 5 sigma for some comparisons, meaning the probability that it is a random error is less than 1 in 3.5 million. This is the threshold at which physics considers something a confirmed discovery. The Hubble tension is not a measurement error waiting to be corrected. It is a confirmed discrepancy with no confirmed explanation. If the early universe measurement is right and the local measurement is wrong, there is a systematic bias somewhere in the distance ladder, an unknown error in the calibration of Cepheids, or an unaccounted for property of Type 1a supernovae. Astronomers have looked hard for this error. They have used independent distance indicators. the tip of the red giant branch method, water masses in distant galaxies, surface brightness fluctuations. The local measurements cluster around 73. The discrepancy does not go away. If the local measurement is right and the early universe measurement is wrong, the standard model of cosmology is missing something. Something that was present in the early universe and affected the acoustic oscillations differently than the model accounts for. Proposals include early dark energy, a component of dark energy that was significant only in the first few 100,000 years and has since diluted away. Or extra radiation from a species of neutrino we have not detected. Or a phase transition in dark energy near the epoch of recombination. Each of these proposals makes specific predictions that can be tested. Each has problems that make it not an obvious solution. The most unsettling possibility is that both measurements are essentially correct, that there is no systematic error, that the standard model is genuinely incomplete, and that the physics of the early universe was meaningfully different from what lambda CDM describes. This would mean the most successful cosmological model in history is missing something real, something that affected the expansion history between the Big Bang and the present in ways we have not accounted for. This possibility is being taken seriously. The instruments being built are in part designed to find the answer. If the Hubble tension is cosmological in origin, if it reflects real new physics, it will leave additional signatures in the large-scale structure of the universe, in the distribution of galaxy clusters, in the weak lensing patterns mapped by Euclid and Roman. Those signatures will either be there or they will not. The answer will come from data. This is where cosmology stands today, a model of extraordinary success and extraordinary tension. A universe whose dominant energy component is unknown. A vacuum whose quantum energy disagrees with the measured value by the largest factor ever seen in physics. An expansion that is accelerating toward one of several possible endings. An observable sphere that is shrinking as a fraction of the total, erasing evidence permanently. And somewhere in all of this, a number, the equation of state parameter W, that we have not yet pinned down precisely enough to know whether the universe ends in cold emptiness or violent dissolution. The instruments working on this problem right now deserve to be named, because they are extraordinary. The Dark Energy Spectroscopic Instrument, DESI, is mapping the three-dimensional positions of 35 million galaxies and quasars using 5,000 robotic fiber positioners that can collectively take spectra simultaneously. Each spectrum gives a redshift, which gives a distance. From these distances, DESI reconstructs the three-dimensional large-scale structure of the universe across the last 12 billion years of cosmic history. It is measuring the acoustic oscillation scale, the characteristic distance imprinted by sound waves in the early universe, at multiple cosmic epochs. Each measurement gives the expansion rate at that time. Together, they trace the history of dark energy. The Euclid Space Telescope was launched in 2023. It is currently mapping the shapes of billions of galaxies with a precision that allows the measurement of weak gravitational lensing. The subtle distortion of galaxy shapes by the gravitational influence of dark matter and dark energy between us and them. The pattern of that lensing encodes the growth rate of cosmic structure over billions of years, which is sensitive to the properties of dark energy. Euclid will produce the most detailed map of dark matter in the universe ever attempted. The Vera C. Rubin Observatory in Chile is beginning the legacy survey of space and time. A 10-year survey that will image the entire southern sky every few nights, cataloging billions of galaxies and discovering millions of transient events, including Type 1a supernovae. The supernovae from LSST will extend the measurement of the expansion history to redshift beyond what was possible before. The distances will be more numerous and more precise. The Nancy Grace Roman Space Telescope, NASA's next large space telescope after James Webb, is designed in part to measure dark energy. It will survey galaxy clustering and weak lensing at high resolution across large areas of sky. It will discover thousands of Type 1a supernovae at distances beyond the reach of ground-based surveys. Its dark energy measurements will be definitive, and the James Webb Space Telescope is already contributing. Its infrared sensitivity allows it to observe Cepheid variable stars in galaxies further away than was possible with Hubble, reducing uncertainties in the distance ladder. Webb's Cepheid measurements are being used to test whether the Hubble tension persists at the new level of precision. The results so far suggest it does. By the mid-2030s, the combined data from all of these instruments will produce a measurement of the equation of state of dark energy and its evolution over time that is many times more precise than anything we have today. If dark energy is evolving, we will know. If the Hubble tension reflects new physics, we will have identified the signatures. The cosmological constant problem will not be solved by telescopes. That requires theoretical physics of a kind we do not yet have. But the observational picture of dark energy will be clarified to a degree that is currently unimaginable. The 2030s may be the decade when we find out whether the universe's fate is cold and long or violent and finite. And there is one more thing. One dimension of this that does not often make it into the popular conversation. The cosmological constant problem, the mismatch between quantum predictions and measured dark energy, is not just a problem for dark energy. It is a problem for our understanding of reality at the most fundamental level. Quantum field theory and general relativity are the two pillars of modern physics. Everything we understand about the universe at the fundamental level sits on one or both of these pillars. They have each been tested with extraordinary precision in their own domains. Quantum field theory describes the behavior of particles and forces at small scales, with an accuracy better than 1 part in 10 billion. General relativity describes the behavior of gravity and spacetime at large scales, with precision tested to parts per billion in observations of binary pulsars, to fractions of a percent in measurements of gravitational wave sources, to extraordinary accuracy in the timing of GPS satellites. But they are incompatible, not in their empirical predictions in the regimes where each has been tested. Both work. But in their conceptual foundations, they describe the universe in ways that cannot be simultaneously true. General relativity describes space-time as a smooth, continuous fabric that responds to the distribution of matter and energy. Quantum mechanics describes matter and energy as fundamentally discrete, probabilistic, and irreducible. In general relativity, you can always ask what is happening at a given point in space at a given time. In quantum mechanics, the uncertainty principle means you cannot. The two theories disagree about the nature of spacetime itself. The vacuum energy problem is where this incompatibility hits hardest. Quantum field theory makes a definite prediction for the energy of the vacuum. General relativity uses that energy to determine the curvature of spacetime. The result should be observable. It is not what we observe, by 120 orders of magnitude. This is not a rounding error. It is a signal that the two theories are somewhere in their foundations, describing incompatible realities. Reconciling them, building a theory of quantum gravity that correctly predicts the vacuum energy and the cosmological constant, is the central unsolved problem of fundamental physics. String theory is the most developed candidate for such a reconciliation. It describes all particles as different vibration modes of fundamental strings at the Planck scale, a length 10 to the power of minus 35 meters, 20 orders of magnitude smaller than a proton. In string theory, extra dimensions of space, curled up at the Planck scale and invisible at all accessible energies, are a necessary feature of the mathematics. The different ways those extra dimensions can be configured produce different low-energy physics. Different values of the cosmological constant. The number of possible configurations is astronomical. Estimates range from 10 to the power of 500 to far larger numbers. In this landscape of possibilities, the anthropic argument finds its natural home. We exist in the configuration that permits our existence. But so far, string theory has not produced a specific, testable prediction for the value of the cosmological constant. It has not solved the problem. It has moved it. Loop quantum gravity, causal set theory, emergent gravity, other approaches to quantum gravity, each make their own suggestions about the vacuum energy. None has produced a satisfying explanation for the 120 order of magnitude discrepancy. The problem stands. It has stood for decades, and it is the same problem as the dark energy problem and the Hubble tension and the future fate of the universe. They are all threads from the same knot. The knot is, what is the vacuum? What is the energy of nothing? Why is the universe the way it is? Here is where we are. We live in a universe whose expansion is accelerating. This is confirmed. The acceleration is caused by something that makes up 68% of all the energy in the universe. We have measured its effects with extraordinary precision across billions of light years and billions of years of cosmic history. We cannot identify what it is. Our best candidate, the cosmological constant, is either exactly right or off by 120 orders of magnitude, depending on which theory you use to calculate it. Our second best candidate, a dynamic field, may be showing its first observational signatures in recent data. The fate of the universe hinges on which is correct. Right now, in the dark, in the silence between breaths, the vacuum that fills the space between the atoms of your body is not empty. It is seething. Virtual particles are flickering in and out of existence. Fields are vibrating at their ground states. The energy density of that vacuum, whatever it truly is right now expanding the universe. It has been doing so for 5 billion years. It will continue doing so for as long as the universe exists. It is the dominant substance of everything. You cannot feel it. You cannot see it. You cannot stop it. The universe is being pulled apart from the inside. The engine is the vacuum. The cause is unknown. The ending, whether cold and final over trillions of years, or violent and complete in tens of billions, depends on a parameter we have not yet pinned down. New instruments are observing it right now. Telescopes mapping billions of galaxies in exquisite detail. Satellites mapping the shapes of galaxies distorted by invisible energy. Spectrographs measuring the redshifts of millions of cosmic traces. Data accumulating in the servers of observatories on mountaintops and in orbit, waiting to be processed into the clearest picture of dark energy ever assembled. The answer is not here yet, but it is coming. And whatever it is, whatever dark energy turns out to be, whatever the vacuum truly contains, whatever fate is encoded in the equation of state of that invisible force that fills all of space, it will be one of the most significant things any civilization has ever discovered about the nature of reality. You are part of the species that is finding it out. You are here in the window. You are here while the evidence is still visible, while the instruments are reaching their full power, while the picture is sharpening. The universe is large. It is mostly dark. Most of it is made of something we do not understand. It is being pulled apart by a force we cannot identify. And we are the creatures on a small warm planet in one of hundreds of billions of galaxies who looked up and noticed. That is the most interesting thing anyone has ever done. The investigation continues. Let us go further back. Further than 1998. Further than Einstein. Because to understand why dark energy is so disturbing, you need to understand just how settled the universe was supposed to be. In the late 19th century, the scientific picture of the cosmos was one of stability and completeness. The laws of thermodynamics had been established. Maxwell had unified electricity and magnetism. Newton's gravity had explained the motions of planets for 2 centuries with precision that bordered on the miraculous. The universe was large, far larger than earlier generations had imagined. But it was comprehensible. It was mechanical. The atoms moved according to fixed rules. The stars burned through some mechanism not yet fully understood. but burn they did, in a sky that was static, eternal, and governed by laws that humans had uncovered through careful observation and mathematics. The universe in 1890 was a place of answers. By 1930, it was a place of questions. In the span of 30 years, the comfortable mechanical universe had been replaced by two theories so strange that their architects sometimes refused to believe their own conclusions. Quantum mechanics said that the position and momentum of a particle could not simultaneously be precisely defined, that an electron had no definite position until you looked at it, that the act of observation altered the thing observed, that particles could be entangled across any distance and behave as though they were a single object. Einstein himself found these conclusions unacceptable. He spent the last decades of his life trying to disprove quantum entanglement. He was wrong. General relativity said that space and time were not a fixed stage on which events played out, but a dynamic fabric that bent and stretched in response to matter and energy. That time ran slower in strong gravitational fields. That massive enough objects would curve space-time so severely that nothing could escape, not even light. Einstein himself found some of these conclusions improbable. When Karl Schwarzschild derived the first exact solution to his equations, the solution that describes what we now call a black hole, Einstein thought it was a mathematical artifact without physical meaning. He was wrong. The 20th century was a sustained lesson in the universe being stranger than human intuition could accommodate. And the lesson has not ended. Dark energy is the latest chapter. It arrived not as a theoretical prediction, but as an observational ambush. Nobody expected it in 1998. Nobody had built the instruments specifically to find it. The supernova teams were looking for a deceleration signal. They found its opposite. And the universe has not explained itself since. There is a quality to the dark energy problem that distinguishes it from other open questions in physics. Most open questions are puzzles within a framework. We do not know how to unify quantum mechanics and general relativity. But both theories work within their own domains, and the puzzle is how to connect them. We do not know the mass of the neutrino with precision, but we understand what a neutrino is, how it interacts, why it has mass at all. The puzzles are hard, but they are defined. You know what a solution would look like. The cosmological constant problem is different. A solution would have to explain why the vacuum energy, calculated from a quantum field theory, is 120 orders of magnitude smaller than predicted. Any proposed mechanism for this cancellation must work across all fields, all particles, all interactions. It must cancel the contributions of the electron field and the quark fields and the W and Z boson fields and the Higgs field and every other field in the standard model, and it must cancel them to 120 decimal places. And then stop. Leave a residue. Exactly the residue we observe. The requirement is so specific that many physicists have concluded it cannot be accidental. Something constrains it. Some principle selects it. But no known principle, no known symmetry, no known mechanism produces this outcome. The door is locked, and we do not have the key. We do not know what material the key is made of. We are not sure what kind of lock it is. Let us think about what it means to not know something at this depth. Ordinary scientific ignorance is localized. We do not know the exact mechanism by which certain superconductors achieve zero electrical resistance at relatively high temperatures. We do not know the precise sequence of events that triggered the Cambrian explosion. We do not know whether there is life on Europa. These are bounded unknowns. We know what we do not know. We can describe the shape of the missing knowledge. The dark energy problem is not like this. It is not that we are missing a piece of the puzzle. It is that we are holding pieces from what appear to be two different puzzles: quantum field theory and general relativity. And they describe the vacuum in ways that are incompatible. The incompatibility shows up with maximum clarity in the cosmological constant. The two theories applied to the same question, what is the energy of the vacuum, give answers that differ by the largest factor ever seen in science. Something is fundamentally wrong at the foundation of our description of reality. This is not a failure of the scientists. It is a signal from the universe. The universe is telling us, through this discrepancy, that our picture of reality is incomplete, that there is a deeper description waiting to be found, that the laws of physics we have, as extraordinarily successful as they are not the last word. This has happened before in the history of physics. Newtonian mechanics was extraordinarily successful for 2 centuries. It predicted the motions of planets, the trajectories of cannonballs, the oscillations of pendulums, the behavior of gases. And then, in 1887, the Michelson-Morley experiment found that the speed of light was the same regardless of the direction of the measurement, regardless of Earth's motion through space. This was incompatible with Newtonian mechanics. Something was wrong. The resolution took 18 years and required Einstein to discard the absolute time and absolute space that Newton's mechanics assumed. The resolution was stranger than anyone expected. The new theory subsumed the old. Newtonian mechanics still works for slow speeds and weak gravity, but it is not fundamental. It is an approximation. The dark energy problem and the cosmological constant problem are suggesting something similar. Our current theories are not fundamental. They are approximations. Extraordinarily good approximations, but approximations. Somewhere below quantum field theory and general relativity, there is a more fundamental description of reality. And from that description, the vacuum energy and its near-perfect cancellation will make sense. The discovery of dark energy from this perspective is not a failure. It is a gift. It is the universe showing us, precisely and quantitatively, exactly where our current description breaks down. It is pointing a finger at the gap between our theories. The gap is 120 orders of magnitude wide. You cannot miss it. You cannot paper over it. You cannot get comfortable with it. You have to solve it. That is what the next generation of physicists is working on. There are approaches worth understanding, even in outline, because they show the direction physics is moving. One approach is called modified gravity. General relativity describes gravity through the Einstein field equations. But the Einstein field equations might not be the final word on gravity any more than Newton's equations were. Modified gravity theories, such as FR gravity, which generalizes the action principle underlying general relativity, can produce accelerating expansion without dark energy at all. In these theories, the modification to gravity at large scales and low curvatures mimics the effect of a cosmological constant. There is no dark energy. There is simply gravity that behaves differently than Einstein's equations predict on cosmological scales. Modified gravity theories make specific predictions that differ from general relativity. The growth rate of cosmic structure, how fast galaxy clusters form over time, depends on how gravity works on large scales. General relativity with dark energy and modified gravity without dark energy predicts slightly different growth rates. The weak lensing surveys from Euclid and Roman will measure this growth rate with enough precision to begin distinguishing between the two. If modified gravity is correct, the answer will show up in the data as a deviation from the standard model prediction. Another approach involves extra dimensions. If space-time has more than 4 dimensions, 3 of space and 1 of time, the extra dimensions might be curled up at scales too small to observe directly. But gravity, unlike the other forces, might leak into these extra dimensions. Gravity felt in our 4-dimensional space-time would be the component of a higher dimensional force. This modification of gravity at very large distances, the scale where the extra dimensions become relevant, could mimic dark energy. Different extra-dimensional models make different predictions about the expansion history of the universe and the growth of structure. Holographic dark energy is another proposal, in certain formulations of quantum gravity inspired by the holographic principle. The idea that the information content of a region of space is proportional to its surface area rather than its volume The dark energy is tied to the size of the causal horizon of the universe. As the universe expands, the horizon grows and the dark energy density changes in a specific way. The model produces an equation of state that evolves over time, the kind of evolution that Deci may be beginning to detect. None of these approaches is confirmed, none has been ruled out. They all make predictions that will be tested in the next decade by the precision measurements now being assembled. The data will arrive. Some proposals will fail. One approach, or something not yet imagined, will survive. That is how physics works. The theories compete. The observations arbitrate. The winner is not the most elegant or the most intuitive. The winner is the one that matches what the universe actually does. And what the universe actually does right now is expand, accelerate, pull everything apart at every scale, from the vast filaments of the cosmic web to the quiet space between the atoms in your hand. The driver is invisible. The mechanism is unknown. The outcome is uncertain. What we know is that the acceleration is real and confirmed. It has been measured by multiple independent teams, with multiple independent methods, at multiple scales. The Nobel Committee in 2011 did not award the prize for speculation. They awarded it for the most carefully measured observational discovery of the modern era. The universe is speeding up. The evidence is beyond dispute. What we know is that the dominant component of the universe, dark energy, interacts with us primarily through the expansion it drives. It does not cluster like matter. It does not form structures. It does not radiate. It does not decay. It fills space uniformly, exerting its influence at every point in the universe simultaneously. You cannot shield yourself from it. You cannot travel to a place where it is not. The room you are in is threaded with it. What we know is that the expansion of space has already placed most of the universe permanently beyond our reach. Not most of the universe in terms of what we can see. We can see billions of light years of galaxies in every direction. But most of the universe in terms of what we can ever interact with. Most of the matter and energy and structure that the universe contains is already and permanently beyond the cosmic horizon. No message we send will ever reach it. No signal from it will ever reach us. What we do not know is why. Why does the vacuum have this energy? Why is it the specific tiny value we measure and not the enormous value quantum field theory predicts? Why did dark energy begin to dominate the expansion approximately 5 billion years ago, roughly when the solar system was forming, roughly when the sun ignited? Is that timing a coincidence, or does it reflect some deep connection between the history of dark energy and the emergence of observers in the universe? The coincidence problem, sometimes called the why now problem, is related to the cosmological constant problem, but distinct from it. The energy density of matter in the universe decreases as the universe expands. There is a fixed amount of matter spread across an ever larger volume. The energy density of dark energy, if it is the cosmological constant, remains fixed per unit volume. At early times, when the universe was smaller and denser, matter dominated. At late times, when the universe is large and diffuse, dark energy dominates. We happen to live at the transition epoch, the moment when matter and dark energy have comparable energy densities. In the past, matter dominated overwhelmingly. In the future, dark energy will dominate overwhelmingly. Right now, it is roughly 32% matter and 68% dark energy. This ratio is special. We are in the window. Is this another anthropic argument? Does life require the transition epoch? Does the period when matter and dark energy are comparable produce the right conditions for stars and planets and observers? Some physicists say yes. The argument is that you need matter domination early to allow structure to form, but not so much matter dominance that dark energy never turns on. We are in the epoch we are in because it is the epoch in which we could exist. Others find this circular and unsatisfying. The coincidence cries out for a dynamical explanation, a physical mechanism that keeps matter and dark energy in roughly comparable amounts over long periods. Such a mechanism would eliminate the coincidence. It would mean we are not in a special epoch because of selection effects, but because dark energy tracks matter in some way. Tracker quintessence models, where the quintessence field evolves to follow the dominant energy component, automatically staying close to the matter density, attempt to provide this, but none have been confirmed. The coincidence problem, the cosmological constant problem, the Hubble tension, the nature of dark energy, the vacuum energy calculation that is wrong by 120 orders of magnitude. These are not separate puzzles, they are facets of the same deep problem, viewed from different angles, and from the center of the problem, if you could stand there, you would be looking at the most fundamental question ever posed about the universe. Why does space have energy? Why does nothing weigh something? Why does the absence of everything, no particles, no radiation, no fields above their ground state, still contain the force that is tearing the universe apart? We do not know. But we are closer than we have ever been to having the tools to find out. Not close in the sense that the answer is around the corner. Close in the sense that the measurements being made right now, in this decade, will either confirm or contradict every major alternative. The space of possible explanations will narrow significantly in the next 10 years. The things we do not know will become more precisely known. The things we have ruled out will be more clearly ruled out. Physics works by elimination as much as by discovery. You build the best model you can. You test it against data. You rule out the alternatives. And at some point, what remains, however strange, must be the truth. The truth about dark energy will be strange. We can say that with some confidence already. The history of cosmology is a history of discoveries that were stranger than the intuitions that preceded them. The expanding universe, the Big Bang, dark matter, inflation, dark energy. Each discovery was initially resisted, then confirmed, then absorbed into the framework, and then found to be the source of new and deeper mysteries. Dark energy is not the last chapter. It is a chapter. A very strange and very important one, happening right now, in real time, in the data streams of instruments pointed at the sky from mountaintops and in orbit. Go outside tonight. Look up. Every galaxy you cannot see, every one of the hundreds of billions out there, too faint and too distant for your eyes, is moving away from you. Has been moving away from you since before the Earth existed. Will continue moving away long after the last star in the Milky Way has burned out. The expansion is not a local phenomenon. It is not something happening out there, somewhere else, in some remote corner of the cosmos. It is everywhere. It is happening inside your room, between you and the wall. The effect is just immeasurably small at these distances because gravity dominates locally. But at cosmological distances, the vacuum wins. Gravity cannot hold the universe together. And whatever the vacuum is, whatever dark energy truly is, it is winning. The universe is larger than it was 1 second ago. It is larger than it was when you started listening to this. It will be larger still when you finish, and whatever is making it larger will continue to make it larger, for as long as the universe exists, in whatever form it takes, through whatever ending eventually comes. The investigation is real. The stakes are real. The mystery is genuine and unresolved, and somewhere in the vast dark between the galaxies, in the quantum hum of the vacuum that fills all of space and determines the fate of everything, the answer exists. We are the species that is looking for it. That is not nothing. There is one more layer to this that belongs in the investigation. One that touches the deepest questions physics has ever confronted. Questions about why anything exists at all, and why it exists in the form it does. The physical constants of the universe. The numbers that appear in the equations of physics as given values that theory cannot derive from first principles, determine whether a universe like ours can exist. The fine structure constant, which governs the strength of the electromagnetic interaction, the ratio of the electron mass to the proton mass, the strength of the nuclear forces, the value of the gravitational constant, and the cosmological constant, the vacuum energy. These numbers are what they are. We measure them. We plug them into equations. The equations give predictions that match the observations. We do not know why the constants have the values they do. We cannot derive them from a more fundamental theory. They are, in our current understanding, arbitrary. But they are not freely arbitrary. Change the fine structure constant by a few percent, and atoms cannot form. Change the ratio of electromagnetic to gravitational force, and stars cannot sustain fusion. Change the mass of the up and down quark slightly, and the stability of the proton disappears. Change the cosmological constant upward by many orders of magnitude, and the universe expands too rapidly for galaxies or stars to ever form. The constants of our universe appear to be finely tuned for the existence of complexity, of stars, planets, chemistry, life. Is this fine-tuning a problem? It depends on who you ask. Some physicists consider it evidence that there is something we do not understand about the origin of the constants, that a future theory of everything will derive them from deeper principles, making them necessary rather than arbitrary. The constants are what they are because they could not be otherwise, given the deeper framework. This is optimistic. It assumes that the apparent fine-tuning will dissolve once we understand things more completely. Other physicists consider the fine-tuning real and irreducible, a feature of the universe that no single universe theory can explain away. The only satisfying explanation, they argue, is the multiverse, an enormous ensemble of universes with different values of all the constants. Most are sterile. Some, the rare ones where the constants happen to fall in the habitable range, produce complexity. We exist in one of the habitable ones because we could not exist in any other. Not because our universe was designed, not because the constants were chosen, but because only in a universe like ours could there be an observer to ask the question. The cosmological constant is the extreme case of this argument. Its observed value requires cancellation to 120 decimal places. If the multiverse explanation is correct, and the landscape of possible universes is large enough, then somewhere in that landscape, there will be universes with cosmological constants close to zero, close enough for stars and planets and observers. We live in such a universe, and we find it mysterious because we are comparing our universe to our theoretical predictions, without accounting for the fact that we could not be in any of the universes where the predictions are correct in the naive sense. This is philosophically coherent. It is also deeply unsatisfying to many physicists because it removes the cosmological constant from the category of things that can be explained by discovering new physics. If the multiverse is the answer, the cosmological constant is not a calculation to be done. It is a selection effect to be accepted. The debate is not resolved. It may not be resolvable within the framework of current physics. Whether the multiverse is a scientific hypothesis, testable in principle through the statistical predictions it makes about the distribution of constants across universes, or a philosophical position that transcends science, is itself a question physicists disagree about. What is clear is this: the cosmological constant forces you to confront the question of why our universe is the way it is at the deepest possible level. It is not a peripheral question. It is not a question that can be answered by building a bigger telescope or running a longer computation. It touches the foundations of what science means, what explanation means, and what it would even look like to understand why the universe exists at all. These are questions humanity has been asking for as long as there have been humans to ask them. For most of that history, the questions were answered with narratives. Creation myths, divine purposes, cosmological stories that placed human beings at the center of a universe made for them. The scientific revolution replaced those narratives, piece by piece with descriptions. Not purposes, but mechanisms. Not stories, but equations. The universe is not made for us. It simply is. And the equations describe what it is, with extraordinary precision. But the cosmological constant problem is where the equations stop being enough. Not because the equations are wrong, but because they give an answer that is either 120 orders of magnitude too large, or if something cancels it nearly perfectly, completely inexplicable in terms of any known mechanism. The equations describe the observation. They do not explain it. And that gap, between description and explanation, between measurement and understanding, is exactly where the next era of physics lives. The people doing this work right now are not detached from the universe they study. They are embedded in it, like everyone else. They use instruments made of atoms whose behavior is governed by the same vacuum energy they are trying to understand. They do their calculations in offices and observatories on a planet orbiting a star in one of the hundreds of billions of galaxies that are right now receding from one another at ever-increasing speed. They are trying to understand the force that is pulling their own existence apart. Slowly, quietly, on timescales that make human history look like a flash of light. There is something extraordinary about this. Not in a vague, poetic sense, but in a precise, literal sense. The universe has produced in at least one location objects complex enough to model the universe, to represent it internally, to build instruments that detect its structure across billions of light years, to write equations that describe its history from the first fraction of a second to the last evaporating black hole, to look at the acceleration of the expansion and ask, why? The universe does not need to be understood. It expands regardless. Dark energy fills every cubic meter of space, whether anyone measures it or not. The vacuum hums with virtual particles, whether anyone detects the Casimir effect or not. The fate that awaits all structure, the long cold death or the violent rip, will arrive on its schedule, independent of whether any conscious entity ever comprehended that it was coming. But somewhere in the fabric of this expanding universe, minds formed. And those minds looked up. And they noticed that the sky was not static, that the galaxies were fleeing, that the vacuum was not empty, that the numbers did not add up. And now they are trying to add them up. The instruments are running. The surveys are underway. The theories are being tested against the data coming in from observatories in Chile and Arizona and California and in orbit above the atmosphere. In the next decade, the picture of dark energy will sharpen. The equation of state will be measured to a precision that will begin to distinguish between the cosmological constant and its alternatives. The Hubble tension will either resolve or deepen into a confirmed signal of new physics. The large-scale structure of the universe will be mapped with a completeness that rivals what we can do today for the local galaxy neighborhood. And then the data will say what it says. Not what we want it to say. Not what any particular theory predicts it should say. What it actually says. That is how science works. It is not pretty. It is not narratively satisfying in the way of stories with clear resolutions. It is slow and iterative and full of surprises and reversals. The history of cosmology in the 20th century is a history of the universe being completely different from what anyone expected. There is no reason to believe the 21st century will be different in that respect. The universe will surprise us again. It always has. Whatever dark energy turns out to be, cosmological constant, quintessence, modified gravity, extra dimensions, something not yet imagined, it will be stranger than what we have now. Because what we have now is a placeholder. Dark energy is the name of a gap in our knowledge. The thing that fills the gap, when we find it, will have a different name. A name that means something. A name attached to a real physical mechanism that we understand, at least partially, at least for now. That name has not been discovered yet. It will be. You are here for the time in between. The time when we know the gap is real and we know it is enormous and we do not yet know what fills it. The time when the instruments are looking and the data is accumulating and the theorists are exploring the mathematical landscape trying to find something that fits. The time when the question is fully formed and the answer is not. This is not a comfortable time. It is the most interesting time imaginable. The universe is accelerating. The vacuum is alive with energy we cannot explain. The fate of everything, every star that will ever burn, every planet that will ever cool, every form of life that will ever think or wonder or measure is written in a parameter we have not yet pinned down. And the investigation continues. Let us take stock of the full picture one final time, because it is worth sitting with. The universe began 13.8 billion years ago, in a state of extraordinary density and temperature. In the first fraction of a second, it underwent a period of exponential expansion called inflation. A phase so rapid that regions of the universe that are now billions of light years apart were once in causal contact, allowing quantum fluctuations in the early universe to see the large-scale structure we observe today. The inflation ended. The universe settled into a phase of ordinary expansion, driven by the thermal energy of the initial event. For the next 9 billion years, the universe expanded and cooled. Matter clumped under gravity. The first stars ignited approximately 200 million years after the Big Bang, illuminating a universe that had until then been dark. The first galaxies formed. The first generations of massive stars lived and died, seeding the universe with heavy elements. Carbon, oxygen, iron, gold that did not exist before. The second and third generations of stars incorporated those elements. Planets formed around them. On at least one planet, the chemistry of carbon-based molecules gave rise to self-replicating structures that became life. For 9 billion years, the universe did what gravity said it should do. Then, 5 billion years ago, dark energy began to dominate. The expansion, which had been decelerating as gravity slowed it, stopped decelerating. The rate of expansion stabilized and then began to increase. Slowly at first, so slowly that it would take billions of years for the effect to become detectable, but persistently, relentlessly. The vacuum energy, whatever it is, had been present all along. It was just too small to compete with the dense, tightly packed matter of the early universe. As the universe expanded and matter diluted, the vacuum energy became relatively more significant. And then it crossed the threshold, and then it took over. 5 billion years ago, the solar system was just forming from a cloud of gas and dust, orbiting a newly ignited sun. The Earth was less than 100 million years old. The first complex life on Earth would not appear for another 3.5 billion years. The first modern humans would not appear for another 4.997 billion years. The 1998 discovery of dark energy would be 4.9999997 billion years away. The force that is now the dominant feature of the universe, the force that is currently pulling every galaxy away from every other galaxy, took over right around the time the building blocks of life on Earth were assembling. This timing has no confirmed significance. It may be coincidence. It may be the anthropic argument in action, that observers can only exist in the window when matter and dark energy are comparable, because earlier the universe was too violent and later it will be too empty. But the numbers are what they are. Dark energy became dominant around the same epoch that our sun and our planet formed. And then, 13.799 billion years later, give or take, some of the atoms that formed on that planet arranged themselves into instruments and pointed them at the sky and measured the recession of distant galaxies and found that the recession was accelerating. And did not know why. That is where we are, not a failure, an achievement, an extraordinary hard-won achievement. The detection of dark energy required the most precise distance measurements in the history of astronomy. It required teams of scientists on multiple continents, independently, cross-checking each other's work. It required the development of space telescopes that could observe supernovae at cosmological distances. It required 30 years of instrument development and calibration and error analysis. And it produced one of the most significant discoveries in the history of science. The dominant component of the universe is something we do not understand. The not understanding is not the end of the story. It is the current chapter. Every previous chapter of this kind, every moment when physics encountered a gap so large it could not ignore it, eventually produced a new theory. Sometimes the theory took decades. Sometimes it required a generation of new instruments. Sometimes it required abandoning assumptions so fundamental that physicists resisted it long after the evidence was clear. But the theory came. Newton's mechanics could not explain the perihelion precession of Mercury. For 40 years, astronomers proposed various workarounds. An undiscovered inner planet, a distortion of the sun's shape, an error in the measurements. None worked. General relativity explained it exactly, as a first test of the new theory. What could not be explained by the old framework was precisely explained by the new one. The ultraviolet catastrophe, the prediction of classical physics that a hot object would radiate infinite energy at short wavelengths, was unexplained for years. The resolution was Planck's quantum hypothesis, introduced as a mathematical trick and later understood as the foundation of quantum mechanics. What appeared to be a minor problem with a radiation formula turned out to be the entry point into a completely new description of matter and energy. The dark energy problem, the cosmological constant problem, these are not minor discrepancies. They are 120 order of magnitude failures. History suggests that when physics is wrong by a factor this large, the resolution requires not a small correction, but a fundamental rethinking. A new framework. Something as different from our current theories as general relativity was from Newton's mechanics, or as quantum mechanics was from classical physics. That new framework does not exist yet, but it is being built, in fragments, by physicists who are working on quantum gravity, string theory, loop quantum gravity, emergent space-time, holographic principles, and approaches that have not yet been named, because they have not yet been discovered. It will not arrive complete and perfect. It will arrive in pieces, tested against data, revised, extended, but it will arrive. And when it does, the cosmological constant will not be a mystery. It will be a consequence, a number that falls out of a calculation as naturally as the Rydberg constant falls out of quantum mechanics. Something that once seemed arbitrary and now seems inevitable. We do not know when that will happen. Science does not work on a schedule. Breakthroughs do not come when they are needed. They come when the ideas and the observations and the mathematics align in the right way. What we do know is that the observations are better than ever, improving faster than ever, and will be far better still by the end of this decade. What we do know is that the theoretical landscape has been mapped with considerable care, and the possible shapes of a solution, even if no specific solution is confirmed, are increasingly constrained. The universe is expanding. That is real. The expansion is accelerating. That is confirmed. Dark energy is real. That is beyond dispute. What dark energy is, that is the question. And it is being asked right now by every major cosmological instrument in operation, by thousands of physicists on every continent, by experiments that will produce data for the next decade and beyond. You exist in the moment when the most important question in cosmology is simultaneously most clearly posed and most actively pursued. The instruments are the best they have ever been. The data is richer than ever. The theoretical ideas are more diverse and more sophisticated than ever. And the answer is not yet known. That is where things stand. The vacuum is filled with something. The universe is being pulled apart. The ending is uncertain. The investigation is ongoing. And somewhere, perhaps not very far from where you are right now, a physicist is looking at data that might, just might, contain the beginning of an answer.